My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 625. In this lecture, I will continue my discussion on Inception Network. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 624. Just see this one, how many outputs we have here. 28 cross 28, isn't it? Just see, size of each kernel is 1 cross 192. We will try to calculate total number of calculations. Just see this one, this is 28 cross 28 cross 16 outputs here, and size of each kernel is 1 cross 192. What is this total number of calculations in first convolution layer? That is basically 28 into 28. Just see, you can understand this. Here I have 28 into 28 into 16. That's what I am writing here. Again 1 into 1 into 1, 1 into 1 into 192. This is about convolutional layer, the first layer. What about second layer? Second layer, the output we are expecting is 28 cross 28 cross 32, and each of my convolutions are of 5 cross. What is my convolution size? 5 cross. Just see, this is output. If you observe carefully, this is output, this is convolution size, 5 cross size of each kernel, 5 cross 16. Therefore, how many calculations? 28 into 28 into 32 into 5 into 5 into 16, isn't it? I sum up these two, isn't it? That's what I am summing up. Just see here, this into this plus this into this. In between I am keeping plus, isn't it? We are adding these two, summing up them, isn't it? After this happens, how many total number of computations you are getting here? You are getting 12.4 million computations. Just if you calculate this one, I will get 12.4 million computations. Even if you want, you can see this one in layer 1. In layer 1, how many computations I am getting here? Just you can observe, this is about 28 into, that is, this is about layer 1. How many? 2.4 million. How many layer 2? 10.10 millions. Total, how many you are getting? You are getting 12.4. You are getting 12.4 millions, isn't it? That's important, isn't it? So what happened with what happened? So I went from 120 million computations to 12.4 million computations using 1 cross 1 kernelization trick. That is important. Which kernelization trick? This is this 1 cross 1 kernelization trick. This point is very, very important. This is also called, just see, this is also called bottleneck layer. Which layer? This is also called as bottleneck layer because this is much smaller. If you compare to this, just see, this is much smaller. If you compare to this, this is just like bottle. Just see, if you can see like this, yes, it is something like bottle sort of thing. This is smaller one, this is bigger one. This is just, you can, that's why they are writing like this. It's something like bottleneck. Just see here, you have bottleneck, isn't it? That's why this particular one is called as bottleneck layer, because this is much smaller. Which one is smaller? This is much smaller. This is larger. Even this is larger. This is small. This is small. This one is small. It is just like bottleneck. That's why they are drawing like bottle. This is like bottleneck layer, isn't it? So this is a very nice software engineering hack. So the Inception modules that they have realized should look like this, isn't it? So the way they do it is like this. Suppose I have output from, let me assume, suppose I have output from previous stage. Let it be. So the way they do it like this. Suppose I have output from the previous stage, which are called previous activations, isn't it? These are the outputs from the previous stages. That is important, isn't it? And I can say, and I have next stages here. This is previous activations. Again, I have next stages, isn't it? This is previous activations, and which one is next stages? Here I can have next stages, isn't it? I get from the previous stages. First, I will perform what am I doing here? What am I doing? First, I will perform 1 cross 1 convolution and create all the values here, isn't it? Then I perform 3 cross 3 convolution via 1 cross 1 convolution, isn't it? Through the bottleneck layer, isn't it? Through the bottleneck layer, as we seen just a while ago. This is much more optimal in terms of number of computations, and then I do 1 cross 1 convolution followed by 5 cross 5 convolution. So this generates some values. Again I perform max pooling. Just I am performing max pooling, and I can perform 1 cross 1. After max pooling, perform 1 cross 1 convolution. All the outputs that I get here, I am doing a channel concatenation, isn't it? What am I doing? I am doing all the outputs that I get here. I am doing all the outputs I am getting here. I am doing channel concatenation. What is the channel concatenation? The outputs are all the same. Just see, the outputs are all the same. 28 by 28. You are getting output are the same, that is 28 by 28. Look at the output, length and width are the same. Length is 28 and width is also 28. That's what it says. Just see, this is length 28, width 28. Length and width are same, that is 28 cross 28. That here the outputs are same. Look at the output, length and width are same. The channel size is changing. That is important here. Here which one is changing? Your channel size. The output get here is what is the channel size here, how it differs, we will try to understand. Your length and width are same, but the channel size is changing. The output that I get here is the input to the next layer, isn't it? The output that I get here is the input to the next layer. This is a cool idea called Inception module, where I am taking the outputs from the previous stage. I am taking outputs from the previous stage and generate input to the next stage. So I get 3D tensor here. Your input size is 3D tensor. Your output is also 3D tensor. In between, I am doing 1 cross 1 convolution. That is important. In between, I am doing 1 cross 1 convolution, 3 cross 3 convolution, 5 cross 5 convolution, and max pooling, and all of them concatenating the result, just like the way we have seen earlier. This is what we want to achieve, but going it directly is very expensive. That's why we are doing it. This module is called the Inception module. When I first read this paper, I said, wow, I think I read this paper somewhere in early 2016. Really, I loved algorithm optimization of trying to achieve 3 by 3 convolution, 5 by 5 convolution, isn't it? They're doing 3 by 3 convolution, 5 by 5 convolution, using 1 cross 1 convolution, all these things in 1 cross 1 convolution in between, isn't it? So the actual Google Inception Net, which is also sometimes referred to as Google Net. Just observe, your L is capital, isn't it? And it is a homage in respect to Jan LeCun's LeNet. This is a 1998 net. So Google named their network Inception Network. So instead of calling it as Google, instead of calling small g, instead of calling small l, just see, here you have small l. If you observe carefully, here your small l, here it is capital L. Yes, with respect to Yahoo LeCun, they named it as instead of writing this small l, they are writing capital L, isn't it? They kept capital L here. So to respect Jan LeCun, it is one of the first very successful deep neural network, and the actual network look like this. Just this is the actual network look like this. This is how the actual networks look. Just observe carefully here in this Google net. You have lots of layers. Look at this. This is your just see the inception modules in this particular architecture. Just see, these are the inception modules. Just see, here I have inception module, here I have inception module, here I have inception module, and he is also explaining softmaxes, isn't it? There are lots of inception modules in your Google net, isn't it? That itself explains importance of your inception network. So all the blue ones are they gave different colors. Just I request you to study this particular architecture. Why? Because it is important. It's important, and it's you can one can realize the importance of this inception networks once if you study this Google net, isn't it? This itself is a fairly large network, but the inception modules is not very hard to understand. Look at this whole network. You have convolutions, you have max pools. If you really want to understand inception module, I recommend you to spend couple of hours going through each of these modules, and just try to browse just try to identify relations between Google net and inception networks, isn't it? So that you can connect the dots. And this whole diagram, actually you can get a full size image here. This is a full size, you know all the building blocks. So what you can do here is you can go to there. You can also find Keras code related to this one in GitHub. As I have time constraints, I am not keeping that Keras code here. You can find in Keras code 2D convolutions, batch normalizations, max poolings. Just go through the code related to this one. You can easily understand in Keras. This picture, just keep this picture in mind and search Keras code in GitHub. Then you will understand it. It is true. Trust me, it is doable. Just go through this. If you have any difficulty, please keep a comment. Thank you very much.